All right, I think we're ready. Welcome back, everyone. Hope you can all hear me. I hope you had a good break. I had a pretty good break. I'm arranging my papers here. I'm in the kitchen. I hope everybody's doing well. I sent an email. Can anybody hear me? Hope you can. I can't see or hear anybody.
No, yeah, we can hear you, Professor.
All right.
I apologize. I'll have my camera on in 1 second.
All right, great. I sent an email a few days ago concerning the test. So the original plan in the syllabus, I don't know if anybody really cares about this, but the original plan was to have the test this week on Friday. But just because we're all remote this week, I would rather do the test a week from Friday. So next week is our next exam. The test, you should expect to be similar to the previous test. It covers everything that we've done since the first exam, so it's not explicitly cumulative, although there's going to be some stuff that you want to still remember how to do, obviously. We'll talk more about the test next week. And I also sent an email yesterday concerning the homework. So the homework shall be due today, as usual, on Wednesday. The issue is that I forgot to post it before the break. I went hard on this break. I didn't really think about schoolwork at all during the break, and I got my COVID vaccine, which made me kind of sick for a day or so. So anyway, the homework will be due today. It's a shorter assignment than usual because we only had 2 days of class last week, and I don't like posting it so late. So if I messed up your schedule by posting it so late, you have my apologies, and you can hand in this homework late if you want to. So I'm just going to say it's due today, but if you can't get it together by today, that's fine with me. Although it is shorter than usual. We will have our quiz on Friday as usual. So it's just going to be about this homework assignment, which is just about the integral test. All right? Anybody have any questions about that or anything else? Excellent. All right, let's get down to it then. So the next section in our book is another type of convergence test. We've talked about, last time was the integral test. This time is something called the comparison test. This is about, if I give you a weird series, can you tell me if it converges or not, right? That's what all the convergence tests are about. They don't tell you what the actual value is when it converges. They just tell you, does it converge or not? And the comparison test is based on comparing the series with some other series that you already know about. It's about, we can compare two different series. All right, the idea is if you already know that some other one converges, then you can compare that one with some other one to show that the other one converges. I'll just tell you what the comparison test says first, and then we'll do some examples. I think the idea of it is pretty simple. So it works, let me just say, it works when we have two series. So I'll call one the sum of AN and another the sum of BN. So if you have two different series, and in order to use the comparison test, they must be positive. That is, the terms on the inside, the ANs and the BN are positive for all n. So the comparison test is only used when the numbers inside the series, the terms themselves, are always positive. There are some variations of the comparison test which you can use in other settings, but this is the one that we're going to talk about. All right, they have to all be positive. In any case, if that's true, then the idea here, and I'm going to write this more formally in a moment, but the idea is if an is less than or equal to b to the, if the terms inside the a's is less than the terms inside the b's, then the sum of the a's is less than the sum of the b's, right? Look at that crazy looking sum sign. This is a wacky one. And what does that mean about the convergence? So in this case, it means if Bn converges, then An converges, right? If the B's, because the sum of the A's is less than the sum of the B's, so if the B's actually does add up to something specific, then the A's must. It's like it's not possible for the A's to like become infinite if it's less than something which is converging. This is the idea of the comparison test. These things must be positive in order for this to be true. Anyway, I'm going to write the comparison test as a theorem. So this is called the comparison test. And here's what it is. There's sort of two parts. Actually, the book calls this the comparison tests, in plural. There's two of them, but anyway, it says this. So this is the one that I was trying to write sort of slightly more informally a moment ago. So it says if the Bn's converges, so if the series using B's converge, and we have An is less than or equal to Bn for all n, then the A's also converge. The sum of An converges, and the sum of the An is actually less than or equal to the sum of the Bn. I'm going to put that last part sort of in parentheses. We are typically not going to make a big deal of that last part, although it's true. The convergence test is typically used just to tell you if something converges or not. That's really what we care about. Although it is true, whatever it converges to will be less than whatever the B's converge to. All right. So if the B's converges and the A's, the terms are less than the B's for all n, then the sum of the A's converges. All right. And then there's another one about things which diverge. This should seem, I hope that this seems pretty clear. What we're just saying is you have a bigger one and a smaller one. If the bigger one actually converges to something, then the smaller one also converges to something. The next one is going to say if the smaller one diverges, that is like if the smaller one becomes infinite, then the bigger one also becomes infinite, which is also kind of obvious if you think about it in the right way. So this one will say if the sum Bn diverges and Bn is less than An. So now we have something which diverges. Since these are positive, it means that it like becomes infinite when you add them all up. And those are smaller than the A's, then the A's also are going to diverge, right? Because if the B's are becoming infinite when you sum them up, and the B's are less than the A's, then the A's will also become infinite. So if Bn diverges and Bn is less than or equal to An, for all n, then the sum An diverges. All right. And there is no parenthetical thing to say about it. If the sum of the B's goes to infinity, and the B's are each less than some other thing, then the sum of those other things also must go to infinity. All right. These two things together is the comparison test, or they are the comparison tests. All right. And the way you use these, so we can use these. So we use these to test convergence of a weird series by comparing it to ones that we already know. All right. So if I show you a series and I ask, and it has to be all positive terms, but if I show you a series which has all positive terms, you can tell me if it converges or not by comparing it, I mean hopefully, comparing it to one of the series that we already know. And those ones, I will just refresh your memory, they're basically in two categories. There's the geometric series. Remember, these have the format a r to the n minus 1. And you have to remember that this converges if absolute value r is less than 1, and it diverges if absolute value r greater than or equal to 1. So this is one possible thing that you might compare your series to. If I give you some weird series, maybe it looks kind of like a geometric, but not exactly. You compare it with the geometric, and whether that geometric has the r in the appropriate range or not tells you if it converges or not. Okay, and then another one that we've talked about is what we call the P series. I think I mentioned this one last time. And that is the sum 1 over n to the power p. And this one converges if p is greater than 1, and it diverges otherwise. All right. So these I mean, by our next test, I will expect you to have memorized this bunch of information here. The geometric series and when it converges, and the P series and when it converges. All right. You have to know these in order to do those comparisons properly. All right, I just want to try some examples. So using the comparison test, you look at a series, you try to compare it with some other series that you already know about, which is these two are the ones that we know about so far, the geometric series and the P series. Let's just try some example here. How about the sum of 2 over n cubed plus 3n plus 7. All right. And the question is, does it converge or not? All right, so we have to decide. We're going to use the comparison test because that's what we're talking about today. I would like to compare this with, and it's always going to be either the geometric series or the P series. And you have to decide, you sort of look at this term here, the form of the term, and decide, does it look more like a geometric or more like a P series? And the simple way to tell is, if you see the n inside an exponent, then you should try to compare it with the geometric. And if you see the n inside, the n as like the base of an exponent, then you should try and compare it with the P series. So maybe I'll write this sort of hot tips, life hacks. You want to compare with the geometric when you see n is in the exponent. All right, and you want to compare with the P series when you see n to some power, right, n to the power p. And what I see in the current example is n to some power with some other stuff. Now there's always going to be some other stuff hanging around, which you have to learn how to deal with. But we will compare with the P series. Now, there's some like extra garbage in there, right? Like I said the P series just because I see this n cubed in the denominator. Now I also see 3n and also 7, but you have to imagine when the n is very, very large, this n cubed is kind of the dominating term. That is to say, the n cubed is a lot more important than the 3n and the 7, right? Sorry, I just stopped talking because I confused myself. What I just said is not true. The n cubed is not the most important here. It's the Sorry, somehow I've confused myself. Give me a moment. Have another cup of coffee. Maybe I should. Yeah, it's fine. Sorry, what I said originally was correct. Sorry. I'm going to compare this with the P series. I'm just going to say it looks like the sum of 2 over n cubed. I'm going to ignore the other parts of the denominator there. It turns out you can't really do anything about the 2, but if it looks like this, which converges, right? Let me say that later. Sorry, I told you I went hard on the break. I haven't thought about this in a week or so. I'm going to compare this one with the P series. It looks to me like 2 over n cubed. I identified n cubed in the denominator because that's kind of when the n is getting very, very large. The n cubed is the one that's bigger than those other things. Anyway, if I want to compare these two terms together, so there's this versus this, right? Can I make an inequality that relates one to the other? Two over n cubed plus 3n plus 7, and then 2 over n cubed. Can you fill in the blank with an inequality? One is less than the other. And this is what I momentarily confused myself about. The one on the left has a bigger denominator, right? Which means the one on the left is smaller as a fraction, right? I think the one on the left has a bigger denominator, and so it is smaller as a fraction, all right? So this can be a little tricky if you're not used to thinking in terms of inequalities, but the reason is because the denominator on left is bigger, right? That's why the fraction on the left is smaller. Okay, so here's my inequality, and then we have to observe that, and the sum 2 over n cubed, this converges. This, of course, is equal to, you can factor the 2 out, and it looks like 2 times the sum 1 over n cubed, and this converges. Why is that? It's because this is the P series where the P equals 3. And remember, the P series converges. P is the exponent on n, which is 3 in this case. The P series converges when P is greater than 1. So P equals 3. That counts as P greater than 1. All right, put them all together. The comparison test says, remember, if we have something smaller than the other thing, and the one which is bigger converges, which it does, then the one which is smaller converges when we take the sum. So by the comparison test, the sum 2 over n cubed plus 3n plus 7 converges. All right. This is using the comparison test. So when you're doing one of these problems, like on the homework, you're going to do a bunch of problems like this. You kind of need to write this sort of important 2 ingredients, right? You indicate the inequality that you're using, first of all, which as part of the comparison test, you need like an less than bn or something like that. And then you also indicate that something or other converges or perhaps diverges. All right, that's the second part there. And then, so if the bigger one converges, then also the smaller one converges. That's what the comparison test says. In the comparison test, if we wanted to show something diverges, you show that the smaller one diverges. That means the bigger one also diverges. All right. Anybody got any questions about this at this point? I'm going to do some more examples, but this is the basic example here. All right, let's try a couple more, and then I got some for you to try. Let's try, how about the sum of sine squared n over n? All right, this is a weird one. Sine squared n over n. This is not what I meant. Sorry, I meant to say, I mean, you could do that also if you want. I meant to say 2 to the n. Sine squared n over 2 to the power n. All right. Now, the sign is very weird, but ignoring that, this looks more like a geometric versus a p-series. Remember, those are our two categories. The geometric is the one in which n is part of the exponent. The p-series is one in which n has some exponent on it, n to some power. In this case, apart from the sign, which that's totally weird, the 2 to the power n makes me think of a geometric. So this thing, I'm going to think of it, looks like maybe just 1 over 2 to the n. I mean, if I just ignore the part that I don't like, which is the sine squared of n, it looks kind of like 1 over 2 to the n. And that's going to be geometric because n is part of the exponent. This, of course, the same as 2 to the power minus n. N is in the exponent. Can we make an inequality then? So between this thing and this thing, I want to write an inequality between them. Sine squared n over 2 to the n. Is it less, is it greater than 1 over 2 to the n? Of course, the denominators here are the same, so you should be looking in the numerators. Anybody want to tell me? Can somebody shout it out? Is the numerator I'm comparing these two numerators here. Which is it? Is the one on the left smaller or is the one on the left bigger?
I'd say the one on the left is bigger.
Why'd you say that?
Because it's a trigonomic function, and I guess you can put anything as n and expand it, but if you just use that 1, it's a constant.
Yeah, you want to think about what could the possible values of sine squared of n be? Of course, that's the same as sine of n squared. This is the same as sine of n squared, right? Could that be more than 1? Or is it always less than 1?
Now that I'm looking at it, I'm saying it can never be more than 1.
Yeah, I think that must always be less than 1. Just because the sine of n is always less than 1, and then you square it, still going to be less than 1. All right, so here actually it is less. The one on the left is less, and that's because since sine squared of n is always less than or equal to 1. It could equal 1. Actually, it couldn't, not if n is a whole number, but whatever. Sine squared of n is less than or equal to 1. All right. Okay, this is our inequality. So this is a common trick. If you see trig functions in there, sines and cosines, they're always less than 1. So you can make this kind of inequality. All right. Maybe I'll just point out the square here is important. It is sine squared of n. The reason the square is important is, remember, in order to use the comparison test at all, these things must always be positive numbers. The sign by itself could be positive or negative, but if we square it, it'll always be positive. And actually, if you don't square it here, you can't use the comparison test anymore, even though the result will be the same, but you can't use the comparison test. All right, what are we going to get here? So this is less than that one. And what about the sum of 1 over 2 to the n? Does that converge or not? Well, this looks like geometric, right? This is 1/2 plus 1/4 plus 1/8 plus 1/16. This is geometric with, remember the geometric series, it converges depending on the r. if the r is greater or lesser than 1 in absolute value, right? And the r is the ratio of each term divided by the previous one. So this is geometric series with the r being something like 1/4 divided by 1/2. It's always the next one divided by the previous one. And this equals 1/2. So it converges. Remember, geometric series converges when the r is less than 1 in absolute value. And so r is 1/2, makes it converge. All right. So put it all together. What we're looking at here is this is smaller than 1/2 to the n, and the 1/2 to the n in the series converges, and so that means the series of the smaller one also converges. So by the comparison test, the series of the smaller one converges. There you go. This is the comparison test. You need to make up an inequality, and then if the bigger one converges, the smaller one also converges. That's what we did here. Any thoughts about that one? I got one more example where it diverges, and then I have some for you all to try out. All right, one more example where this one diverges. Although you're not going to know that, when I just tell you the problem out of nowhere. But it's true. This one diverges. All right. Now, when you see this, you should, just like before, think about what am I going to compare this to? To what shall I compare? The thing on the inside there. Well, the cosine there is always going to be less than 1 and greater than 0. This one looks to me like just something like 1/n, or maybe 2/n. If you take the largest possible value the cosine could be would be 2. The smallest possible value would be 0, right? Cosine squared has to be greater or equal to 0. This looks something like 1/n or maybe 2/n. And we know the sum of 1/n diverges. That's because that's the p series with p equal 1. And that diverges. All right. What if I make an inequality then? Cosine squared n plus 1/n. This actually will be greater than 1/n, right? Just because the numerator on the left side is bigger. It has an extra thing in it, right? The numerator on the right side is just 1. The numerator on the left side is like a little bit bigger than 1. Okay, so the term on the left is bigger than the 1/n. So cosine squared of n plus 1/n is greater than 1/n, and the sum 1/n diverges. I just said that, but I'll say it again. That's because this is the p series with p equals 1, right? The p series is 1/n to the p. And the p is 1 in this case. And so, remember the p series converges when p is more than 1, and it diverges when p is less than or equal to 1. So here it's 1, so it diverges. All right. And so what we have in our inequality is the smaller one diverges, which means automatically the bigger one also diverges. So I will say by the comparison test, the bigger one also diverges. Cosine squared n plus 1/n diverges. All right. These can be a little tricky because you have to have some kind of creativity or something. Like you have to be able to look at this and realize that what I should be comparing this with is 1/n, which is a little, I don't know, a little tricky, right? You could say this is less than 2/n. It's true. The biggest this could possibly be would be 2. But 2/n diverges, and to say something is less than something which diverges, that doesn't mean anything according to the comparison test. You need to say the smaller one diverges, then that means the bigger one diverges. If you can show the bigger one diverges, that doesn't mean anything about the smaller one. All right. This is the comparison test. I'm going to give you some to try out. What happened? I just lost my connection. Coming back. Come on, bruh. What you doing? I'm back. I don't know what just happened. Am I back? Anybody hear me?
We can't hear you, Professor.
You can? All right. My Zoom just disconnected. Oh, I'm muted. Okay. Am I here now? Somehow
Yes, yeah, I can hear you.
my Zoom just disconnected. I don't know what happened. But I'm back now. I'm ready for action. So I got a few for you all to try. See what you think about this. Here are 3 series. So I would like you to look at each of them and tell me if they converge or diverge. And here's my hint. One converges, one diverges, and then one, actually, one is sort of a trick question. For one of them, you are not allowed to use the comparison test. So one can't be done with the comparison test. All right. See what you think. So one of them you just have to say you can't do that one. The other 2 you can do. One of them converges, the other one diverges. I would like to give you some time to do these, and I thought maybe you know, this is the time in which I would ordinarily walk around the room and see how everybody's doing with it. I want to try and simulate that, so I'm going to put you all in. All right, let's talk about these. So these are a little tricky in my opinion. The first one, I hope you said it converges. The first one, you want to, in your inequalities, sort of get rid of part which looks more complicated. And in this case, since they're in the denominators, the appropriate inequality to use for the first one is like this: 1 over 4 to the n plus root n. I don't like the looks of that root n, so I am going to throw it away and just turn it into 1 over 4 to the n. And the inequality goes this way around. The thing on the left is less because its denominator is greater, right? So when you throw away something from a denominator, the fraction, you know, gets bigger, right? The thing on the left is less than the thing on the right. And then the thing on the right converges, though. So I will say also 1 over 4 to the n. This converges. This, of course, is 1/4 plus 1/16 plus 1, whatever the next power of 4 is, 64. This is geometric with r equals 1/4. All right? Each one divided by the previous one is a ratio of 1/4. And so it converges. And so the smaller one in a series also converges. This is what you should have said for that first one there. All right. You compare it with 1 over 4 to the n. 1 over 4 to the n, the series converges because it's geometric with r as 1/4. And so that means the smaller one, the one you started with, also converges. Any questions about that one? I hope that one worked out for folks. Okay, what about the other 2? I said one converges, that's this one, converges. One diverges and one is not allowed to use the comparison test. Can anybody tell me which one cannot be done using the comparison test? You got two choices. Anybody have a good reason to rule out one of the other two?
Well, the second one diverges, right? Since it's 1 over n, so then the last one can't be done.
Yes, that's correct. Do you have a reason why you can't do the last one, or just process of elimination?
Oh, yeah, it looks tricky.
It looks a little weird. Yeah, actually, remember the comparison test. When I say it can't be done, I don't mean just like it's too hard to do, but I mean actually the comparison test does not apply to that one. And it's because, remember, the comparison test can only be used when the terms are all positive. And in that last one, some of these are going to be negative, when in fact most of them will be negative, because n squared is typically bigger than n, and so that numerator will be negative. So this one actually can't be done because it's not positive. Not positive terms, right? The terms in there are typically going to be negative because n minus n squared is usually negative. And so that last one there, you can't use the comparison test. Not because it's too hard, but because it really just straight up doesn't work. Okay, in our remaining 2.5 minutes, let's just do the middle one, diverges. Why is that? I think actually she just said 1 plus log n over n. Now, you should look at this and say, I don't like that natural log of n. So what I want to do is an inequality between these two things, right? And the one on the left is bigger because it's just 1 plus the natural log of n. The natural log of n is some positive number when n is bigger than 1. So this is greater on the left because its numerator is bigger than 1. All right? And 1 over n, the series, diverges because this is a p-series with p equal 1. All right? Just like one of the examples we did a few minutes ago had this same thing. So what we see here is the smaller one diverges, which means the bigger one also diverges. So the sum 1 plus log n over n also diverges. All right, this is the comparison test. A little tricky. There's actually a related trick which makes these sometimes slightly easier. So next time we're going to talk about a sort of variation on the comparison test which can sometimes make things a little bit easier. But this is the basic sort of bare bones comparison test. All right, and I think that'll do it for us today. So homework is due today. If you do it late, that's fine, but we are going to have our quiz on Friday based on the homework for today. All right, I think that's that. Welcome back. See you all on Friday.
Thank you. Thank you.
Thank you.
Bye-bye.
Professor,
Yes.
so is the exam is going to be from homework 5 to homework 9?
Let me just look at my calendar here. It's going to include what we do on Friday this week, but nothing else. I don't know. You were here at the beginning when I said the exam is going to be next week instead of this week, right?
Yeah, yes, I did.
Yeah, right.
You also said like it was the content from after last exam until
that's right.
This week, or also including stuff we learn next week.
Not including what we learn next week. So yeah, just everything. So yeah, what you said before is correct. Homework 5 through actually 5 through 10. So homework 10 will cover what we did today plus what we do on Friday.
All right, thank you.
Yep. All right. See you.
Okay.